All right, welcome back. So in the previous video, we talked about what the root test is. Now we want to actually start using it to check convergence of a series. So first one I want to look at here is this sum as k goes from 1 to infinity of k squared over 2 to the k. And we worked that out previously, actually, with the ratio test. We actually looked at that one with the ratio test. And we were eventually able to get to the result that the limit of by the ratio test was 1/2, which was less than 1, and so we were able to say that series converged. Okay, and you can kind of compare the work that we did here with the ratio test to the work we're going to need to do with the root test. And you can kind of judge for yourself whether this one here would be better done with the root test or better done with the ratio test. So you can kind of maybe judge for yourself afterwards. Okay, so let's approach this now with the root test. So for the root test, we take the kth root of the absolute value of this stuff. Well, since k squared is always positive and k is 1 or bigger, and 2 to the k is positive, once again, we don't need to use the absolute value here. Okay, so we just say rho is the limit as k goes to infinity of the kth root of this stuff, k squared over 2 to the k. Now, remember what it means to take the kth root of something, right? What's it mean to take the kth root of something? That means, in terms of an exponent, to raise it to the 1 over k power. 1 over k power. So on top here, this would be limit as k goes to infinity of k squared raised to the 1 over k power. That would actually simplify to k to the 2 over k power. In the bottom, kth root of 2 to the k. This is why we often like the root test when we're dealing with powers of k, right? Kth root of 2 to the k, that's just going to be 2. So now the question is, what about this thing? What about this thing? Well, we have to deal with this limit of k to the 2 over k power. Right? We have to deal with this limit of k to the 2 over k power. Okay. Well, what do we have there? How do we compute that? So I'm going to step aside because it's actually not just a simple one-step thing to finish this answer here. Because k to the 2 out of k is actually a limit of the form infinity raised to the 0 power. Right? It's one of our indeterminate forms. So it's not going to be as simple as, oh, the answer is just this. Right? We are going to have to do some work here. So remember, when we compute a limit of the form infinity to the 0, or the other one's 1 to the infinity, or 0 to the 0, the exponential ones, remember what we do is we take the limit of the outlet of that stuff. The limit as k goes to infinity of the ln of k to the 2 over k. And then using our properties of logarithms, we can bring that 2 over k out. We'll have 2 over k times the ln of k, which at this point is now a 0, because as k goes to infinity, 2 over k goes to the 0 power, times infinity limit, a 0 times infinity limit. So remember the approach to working with something like that, when you have 0 times infinity or infinity times 0, is to take one of these things and write it over the reciprocal of the other. So life is much easier if we put ln up top. So ln over the reciprocal of k 2 over k. That would be k over 2. Right? And at this point, we've now transformed this into an infinity over infinity limit, so we can invoke L'Hopital's rule. Limit as k goes to infinity, we take the derivative 1 over k over 1/2. And just doing a tiny little bit of simplifying. The limit as k goes to infinity of 2 over k. Of course, as k goes to infinity, that goes to 0. That goes to 0. So the limit of the ln goes to 0. So that means that the limit of, as k goes to infinity, of k to the 2 over k goes to e to the 0, which is 1. Okay, so going back up here now, this limit as k goes to infinity of k to the 2 over k over 2. Right, that was our problem. Well, k to the 2 over k goes to 1. Okay, so k to the 2 over k goes to 1. And so therefore, this would be 1 over 2. Right, because this limit here, again, is going to 1. And so the limit is 1/2. Coincidentally, the same as the limit we got with the ratio test. So both the ratio and the root are both going to 1/2, which is less than 1. And so, therefore, by the ratio or the root test, this series converges. This series does actually converge. Of course, we knew it already converged because we did it earlier with the ratio test, but now we've seen that we're able to do it as well with the root test. And you can kind of judge for yourself whether you think this would have been better with the ratio test or whether this would have been better with the root test. Here, we did have this extra work that kind of really made our root test a lot longer. Right, having to work out that limit as k goes to infinity of k to the 2 over k. So there is that bit that definitely added to the length of the problem. So you can kind of judge for yourself. The root test also, though, did have, you go back, it did have a few extra pieces involved too. So yeah, you can judge for yourself. Probably I'd say ratio test was probably a little bit easier on this particular one, but just by a little bit.